Hello again, it's been a while. I'm still fooling around with resistors and there's more to come. And with all that, when I measure resistors, I've always got to wonder how accurate my meter is. So in an effort to try and get some definitive handle on how accurate it is, I've got these precision resistors installed in a box. There's 1 ohm, 10 ohm, 100 ohm, 1k, 10k, 100k, 1 meg, 10 meg. And they're arranged in Kelvin connections, so there's sense terminals on the red and the black. The force terminals come in individually for each, the force high, individually to each resistor on the red, and all the blacks common up to a common force low terminal. The sense terminals are 19mm, 3/4 of an inch apart for connectors like that to go in. So you put in, there's a sense of that for that resistor, and then connect the force high and force low. It's in a diecast box, and there's metal blocks in there that each resistor is vaguely connected to thermally, so that they're all pretty much at this, well, in an attempt to make the resistors all at the same temperature as the box. There's also a couple of temperature sensors in there coming up to these terminals. Haven't done anything with that yet. Did I mention, yeah, case ground terminal for the case itself, but otherwise everything else is isolated from the case. I'll flash up the schematic for this thing, and then the rest of the video is about the construction of it and a bit of testing at the end. Right, so here's my kit of parts. The resistors, obviously. The two lowest values are in 4-wire TO220 packages from Vichy. The two highest are in ceramic packages from Caddock, and the four in between are also from Vichy in plastic packages. And the box, obviously, with all its holes drilled in the lid, and the box, screws to hold it together. I've made a neoprene gasket to try and keep the humidity in there constant. This box wasn't the type with the groove and the rubber liner that you could put in to make it IP66 rated. So this will work pretty good, I think. Then there's the temperature spreaders and mounts for the resistors. Banana terminals, well, I've got one for the case ground. The sense terminals, I've used these Pomona ones. They're gold plated, they cost about $6 a shot. And for the force terminals, I've used cheaper ones, they're still I think $1 something each, but they do seem to have literally a silver lining, because force isn't so important as the sense. I've got a force high for each resistor and a common force low for all of them. Some hookup wire, the label, and because heat spreaders are going to be bolted with these countersink screws, and then they'll be covered with the label, there's no way, you don't want these to come loose. I'm not going to put spring washer on there because I want the spreader to be in good contact with the lid. So I'm going to put Loctite on these so that they won't work loose. And on the box, I'll probably put one or two of these down here with wires going up to temperature sensor on one of the spreaders. So there's my kit of parts. Let's have a look at the resistors more closely. Here's my resistors: 1R, 10R, 100R, 1K, 10K, 100K, 1 meg, 10 meg. The other side I think just has date codes and part numbers. Now these resistors cost between $45 and $75 Australian each, so I'd like to thank Vichy and Caddock for providing these resistors free of charge. Oh, no they didn't, did they? They only do that when you've got thousands of subscribers. this shitty little channel just doesn't cut it. Oh well. Oh, Patreon supporters. I'd like to thank my Patreon supporters for providing the funds to... Oh, no Patreon either. Fuck. I have to pay for these things myself. Oh, YouTube monetizer. Damn. Oh well. It's only money, isn't it? So, time to start putting it together, I think. So there it is with the heat spreaders screwed on and Loctited. And the next thing is to punch holes like that using these things, make holes for all the terminals to go through. And you may notice there's a difference between these two. I'd actually done it all, stuck it down and everything, and made the mistake of these outer circles being about the size of the terminal surround, so that even a small error showed up as, you know, a line sticking out the side somewhere. So that was pretty terrible. And there was a couple of blemishes which I think was Loctite seeping out of these screws. So I've done it again with smaller holes, so I've just got to punch the holes in this, cut it to size and stick it down again. I'll show you that when I've done it. So here's Mark II of this label. Smaller holes. The rings don't show around the terminals now, except I forgot to do this one down here. So however bad it is however bad it is. And the blemishes that were there are gone, and it's been coated with clear gloss many times. So I'm about to put on the terminals. These little nicks you can see on the centre row for the force terminals, just filed in there, therefore, I don't know if it shows up on camera, but there's a little nick there, so that will, it's quite locked in place there, so that's what that nick's for. Alright, I'll put them all on. So there it is with the terminals all installed. Looks pretty nice, I reckon. And there's a bolt there which had to go in before that terminal. That's going to be for the temperature sensors. I'm going to make a little circuit board that goes on that. And the connection to the outside world for the temperature sensors, I was going to use this or two of these. I decided to scrub that and put in a 5-way, I suppose it's some sort of DIN socket. And there's the plug for it. So I want to have two temperature sensors in there, and LM35DZ analog output and DS18B20 with a digital output, just for comparison, just have two, and it'd be interesting to see how well they match each other too. So I think the next thing is to actually mount all the resistors. Let's do that. Right, there they are all mounted. And just by the way, I think I got lucky with where I put that. I should have perhaps put it so that it would be over this area where there's no interference. It's going to be here. It interferes with that, so it's got to be at this end. And it just clears it, so I think I'll be okay. Now, mounting the resistors, the two in the TO220 packages is just bolted down as per normal. The heatsink part of the package is isolated from the resistant part. The other four are just held down by a cable tie, but the packages have a tendency to tilt, so there's a bit of just cotton bud tubing in there to give a slight increase in tension and to press the package against the heat spreader. Now for the ceramic, similar thing, cable tie with a bit of a tubing to keep it flat against the aluminium, but I didn't like the idea of fragile ceramic being pressed against the aluminium directly, so I put some silicone insulation material, as you'd use on a power transistor, in there just to cushion it a little bit. And also because these are higher, I've added some extra aluminium just super glued onto the bottom piece. So that's how I've mounted them, and still to wire it up, of course. Now none of this has any thermal insulation from the heat spreader to the resistor, and my reasoning for that is very similar to how, or analogous to how this is going to be used to measure resistance. The sense wires going to a voltmeter, it doesn't matter if the sense wires have some resistance, because the current is only what's required to run the voltmeter, which is minute. So tiny current, even though there's resistance, there'll be negligible voltage drop and the voltmeter will read the correct value. Likewise here, these things, the resistors are never going to have much current running through them. They won't be producing much heat, if at all. So these things are not heat sinks. The idea of them is just to spread the temperature of the ambient box into the resistor. So the only heat flow, which corresponds to current, is what's needed to equalise the temperature between the low thermal mass of the resistor and the big thermal mass of the block. So very low current, so even though there might be a high thermal resistance there, the temperature difference, which corresponds to voltage drop, should be small too. That's my theory anyway. Now I've just got to wire it up. These are going to be pretty easy, obviously. These should be okay too. These are a bit tricky. I've experimented. I'm going to have to bend those carefully down to there. Yeah. I wish they had longer wires on these things. But yeah, now of course we don't want to overstress the resistors by soldering temperatures getting into them, so what I'm going to do is try and clamp them. I've just got a pair of pliers with a cable tie over them, so I can put it onto a wire there and then push this up so it's clamped onto the wire, so that when I solder this end, this will absorb all the heat and none will get into the resistor. That's the theory anyway. See how well it works out trying to do it. Alright, there it is with the resistors wired up. Haven't done anything for about a month and a half on this after that, because as usual, struggling with motivation, and also had a dose of the COVID, just a mild one. But anyway, back into it now. So there's that wired up. We have each resistor going to the 2 sense terminals and then up to the high force terminal, and a common low terminal going all the way around, or up here and up there, and a ground terminal. And then there's the case. This is the alternate connector I decided to use. I had a neoprene gasket in there, but there's not enough thread on that to hold it down properly, so I've ditched that. There's a spring washer under there, and I'll hot melt some glue all over that once I put the wires on these. And I've made the temperature sensor board, which will go onto that screw there. Bit of a cock up with the hole positioning. Ideally this would be a right angle, but I didn't have any of those. But anyway, it's just an LM35 temperature sensor analog and a DS180B20 digital temperature sensor. Reverse protection diodes, so if the volts come in backwards, it'll burn out whatever sent them here, and just a local supply capacitor. So I'll put that on and wire up this. Alright, there it is with the circuit board mounted there. I don't know why the hell I put that hole there instead of in the middle of the bar. In fact, I did. You might have noticed earlier that I had started a hole there and then decided to move it across, which is just stupid because it made it really hard to get that board on. But anyway, it's there now. I also had to change that capacitor because it interfered against that post. There's a pile of hot melt glue there to hold the wires in place and maybe stop this thing from loosening. I didn't show the bottom before. I've got all the resistor types and values and parameters and some foots. So there it is. I'll screw it together. So I'll screw that up and hopefully never open it again. Right, done. Let's take some measurements just of the resistors. I won't do the temperature interface bizzo yet. That'll come later when I try and vary temperatures a bit and then also log it on 6.5 digit meter, and to do that I'll also need to make a HPIB or GPIB interface for the meter, so won't worry about temperatures just yet. Bit of dirty paw prints from holding it like that. There's little I can do about that. I tried cleaning it off but I can't, and replacing this with something more protected would entail pulling the whole thing completely apart and starting again, so I'm just going to have to put up with it. Anyway, let's put it on a meter and see how accurate it is, or how accurate the meter is. That's the trouble with these things, you never know what you're measuring. Well, let's try it. Right, here we are. I've got 2 meters, they're both warmed up. I want to keep this one warmed up even though I'm not using it. This is the one that I trust the most, and we're looking at the 1 ohm at the moment. We've got the force low going into the common for that, and then for each resistor we put the high in the appropriate of those yellow connectors, and the sense is on this with screen cable. It might help keep some noise out, and this goes down to another instrument which has got a ground terminal, so it's grounding to the case. Now this thing looks like a banana socket, but it's not, but at least it has a hole in it that will take a banana plug, so I can screw that down and make a ground connection anyway. So there we are at 1 ohm. Now I've got a copy of the label I put on the back, and I put on them underneath each power rating. I put the voltage and or the current that would cause that power to be dissipated, so I know what the maximum voltage and current I can run through it is. What I should have done also is, underneath the tolerance, is worked out how many ohms that represents, and I've done that here. So for 1 ohm, 0.02%, that means 0.002 ohms, fifth of a milliohm, and 0.0002, that's out of tolerance. It should be 0.9998 at the lowest, or 1.0002 at the highest. Then again, the temperature is currently 16.5 degrees Celsius, so not probably 20 to 25 degrees that these would be specified at, I imagine. Anyway, so yeah, not perfect, still good though. Let's go to 10 ohms. So we move the sense and the high force. Let the meter catch up, there we go, and that should be within a milliohm. And that's very much within a milliohm, third of a milliohm. Drifting down, that's right on the border. Okay, 100 ohms, that should be within 5 milliohms, just inside. Again, this is 16.5, it's probably specified more in the 20 to 25 degrees range. And it looks like the battery in my camera's dying. It's only given me a couple of minutes before it flattens, no matter how long I'll charge it for. So anyway, we've just switched to the 1K, and that should be within 0.05 ohms, and 0.05, yes, that's good. They're all on the low side. I wonder if that's because it's pretty cool in here. Okay, up to the 10K, 10.001, that should be within 0.5 of an ohm, so it's well within. That's pretty good, isn't it? That's very good. I'm rushing through this because the battery on the camera might flatten at any time. Up to the 100K, should be within 10 ohms. Oh, that's more than 10 ohms out, isn't it? 1 meg should be within 100 ohms. That digit there, so that's within 100 ohms. And finally the 10 meg, which should be within a K. So that's within a K. That's pretty good. Hopefully I can try and characterise this thing a bit better in the future. It'd be nice to get a hold of a calibrated meter to measure it on, but you know, I'll try and get a good handle on how much these things drift around with temperature and stuff. I've got some plans on how to do that. But yeah, for the moment that'll have to do. And I've just got one little experiment I want to try. I've got this DC voltage source connected to this meter, so I'm just measuring what comes out of that. This thing's not calibrated fully, so I have to adjust this to get a particular voltage there. So I'm trying to get 11 volts there exactly, and I have to put in that to get it. Now that is then going to this guy. I've got the positive going into the high of the 10k, so it's going through the 10k and then through the common force low and then through the 1k resistor to the negative. And I'm measuring the voltage across the 1k resistor because meters are better at measuring voltage than resistance. So if I make that 11 volts, we've got 10k plus 1k is 11k, so we should get 111 for 1 volt precisely across here. So take this out of standby and let this thing catch up, and that's about as close as I can get it. Well, that's pretty close to 11, isn't it? The last digit drifts up and down a bit. And I'm running this at, the 1k can take 24 volts, so 1 volt is nothing, and the 10k can take 77 volts, so you know, with 10 volts across it, it's running at 1/8 of its capability, so it shouldn't be getting too warm. I'll grab a screenshot and calculate how close that 1 volt is to what it should be given the incoming voltage. That's with 10k and 1k. Let's try 1k and 100 ohms. So again, we should be getting 1 volt. I'll do a calculation based on those numbers. This resistance is a bit too low, so let's go up to 100k and measure across the 10k. And there we go with the 100k and 10k. That's as close as I can get to 11. And the resistance of this on this range, the input impedance is well into the gig ohms, so sitting across the resistor we're measuring has no effect. And yeah, so I'll do the calculations on these. I'll put them on the screen. And I hope you found that interesting. Catch you later.